So when we've talked about spontaneity before, we've talked about delta G. Well, delta G still applies here. If I put reactants on a shelf and products on a shelf, because the delta G for this reaction between zinc and copper, because the delta G goes down from products to reactants on my plot, the reaction is spontaneous. It's negative 212 kilojoules per mole. As I said before, electrochemistry is where we can get some useful energy out of the reactions we've been discussing. Scientists measure this useful energy in voltage. A volt is a joule over a charge. The delta G equation that relates voltage and spontaneity is negative NFE, where N is equal to the number of electrons. There are 2 electrons exchanged in that reaction. F is Faraday's constant. It converts between joules and volts. And then E is the voltage that is measured over that reaction. So if you were paying attention to the last formula, hopefully you noticed that delta G equals negative NFE. And remember, negative delta G means spontaneous. So positive E will indicate spontaneity. We're going to use reduction potential tables like this in a lot of the questions throughout this electrochemistry section. Note, every single reaction in that list is a reduction reaction. Does it mean these things can't be oxidized? No, it just means we'll change how we use the equation. You'll see what I mean momentarily. Well, let's use that reduction potential table to answer the question, will platinum solid reduce nickel 2+? So if platinum solid is going to reduce nickel, that means platinum itself will be oxidized. So here is an oxidation half reaction for platinum, where platinum solid is going to lose 2 electrons to become platinum 2+. What happens to those 2 electrons? They go onto the nickel. Nickel 2+ will gain those same 2 electrons that platinum lost in order to become nickel solid. But the question is, does this reaction happen spontaneously? Do electrons prefer to be on platinum or do they prefer to be on nickel? If I look at the voltage from my reduction potential table, note that I wrote the oxidation equation for platinum here, which is the reverse of this top reaction. So I need to change the sign of my reduction potential. The reduction potential of platinum is positive 1.2. Therefore, the oxidation potential is negative 1.2. Nickel is written exactly as found in the table, so we just bring that value down as negative 0.25. If you sum those reactions, you'll get this, and you'll get negative 1.45 volts. A negative voltage means non-spontaneous. This reaction is non-spontaneous. So if we think about that on an energy plot, what that means is the reactants are lower energy than the products. It gives you a positive delta G. It also means electrons prefer to be on platinum rather than nickel. Electrons are more stable on platinum than they are on nickel. Let's work on another example. Will strontium reduce silver plus? So that's going to mean strontium loses electrons to give them to silver. So here is the half reaction where strontium is losing electrons, 2 of them. And here's the half reaction where silver is gaining them. But wait, silver is only a +1 ion. So we need 2 silver +1s to balance out the 2 electrons that strontium gives away. So then if I consider is this reaction spontaneous or not, I'm going to look at my voltage. Looking at my strontium reaction up here, the reduction potential of strontium is negative 2.89. But since my equation has strontium being oxidized, I change the sign, positive 2.89. The reduction potential table up here for silver has silver gaining an electron. I'm pulling that down without changing anything, 0.8 volts. Summing that reaction together, I get my overall reaction here and an overall voltage of 3.69 volts. It is absolutely a spontaneous reaction. So we can go through this entire sequence of making half reactions and adding up cell potentials multiple times to see if this reaction is spontaneous. But we can also use the reduction potential to our advantage to take a little shortcut. If we find the reactant, metal, and draw an arrow to the reactant ion, as given down here in our equation, If that arrow points up, the diagonal rule says yes, the metal at the bottom is capable of reducing the ion that's above it. Diagonal rule. We can use the diagonal rule to evaluate whether magnesium will reduce copper. Since the metal is a product below the ion, the answer is yes. That reaction does happen. Magnesium can reduce copper 2+. We can also use these potential tables to evaluate reduction strength or oxidation strength or oxidizing agent strength or reducing agent strength. If we know the pattern that the higher you go up the list on the reactant side, the more badly that ion wants electrons. Those are all oxidizing agents on the reactants side. Everything on the product side, you can think about wanting to give away electrons. The thing at the top of the list is the most selfish. Platinum is most selfish. Strontium is most generous. Those are all reducing agents. So you can very easily answer questions like, which species is the best reducing agent? That would be strontium. Which species is the worst reducing agent? That would be platinum. And really, because we want to make sure you guys aren't thinking of these as ions, I'm going to tell you it's platinum solid and strontium solid. Will H+ oxidize silver solid? We've talked about the diagonal rule. If the metal is below the ion, that's a reduces. The way it works for the other way around is if the ion is above the metal, that's oxidizes. So will H+ oxidize Ag+? We find H+, and we have to go up to try and oxidize? Nope. That one doesn't work. That one would give you a negative 0.8 electron volts. That's no good. What metals do react with HCl? Because of this oxidizes rule, we're really looking at all of the metals below H+. So that's nickel, magnesium, and strontium. What will oxidize Ag2+? I've only given you a partial table here, but on this table, the only thing capable of oxidizing silver is platinum 2+. So we saw in that little clip that a metal bar can be inserted in a solution that has metal ions. And if the reaction is spontaneous, after some time, the bar will dissolve and your metal ions will precipitate. Here's another example between cobalt and zinc. That's a spontaneous reaction. The reaction between zinc and copper is a spontaneous reaction. We can actually use these three reactions in comparison to come up with our own reduction potential table. So we can write out the reduction reaction for copper, and we can compare a couple of things. This reaction compared to that reaction, copper takes electrons from cobalt, and copper takes electrons from zinc. So it means copper is more easily reduced than cobalt or zinc. So it would belong highest on our list here. If I then compare the two cobalt reactions here and here, in this top one, cobalt is giving up electrons to copper. So electrons are more stable on copper than they are cobalt. And in this middle one, zinc is giving up electrons to cobalt. So that means electrons are more stable on cobalt than they are on zinc. So I put cobalt next in my reduction potential table. And finally, because there's only three metals in consideration here, zinc is the least likely to be reduced. The electrons are least stable on zinc of these three metals. All right.